On the next episode of TechThreads, Weaving the Intelligent Future, we're excited to welcome a guest that needs no introduction. Jim Keller, the legendary chip architect behind AMD's Zen, Apple A series, Tesla's autopilot hardware, and now Tenstorrent's AI vision, joins us in a raw, insightful conversation on how compute, connectivity, chiplets, creativity, and cross-continental collaboration are reshaping the future of AI.
Welcome to TechThreads, Weaving the Intelligent Future, the podcast exploring the fast-paced world of technology. In each episode, we dive into the latest innovations in data movement, AI acceleration, and the transformative potential of chiplet technology. Join us as we explore the breakthroughs that shape the future of computing and hear from industry experts on what's coming next in the tech landscape.
Hello, and welcome back to TechThreads. I'm Nandan Nayampally, Chief Commercial Officer at Baya Systems, and today we're privileged to have a guest that needs no introduction, but it's just amazing to look back at his achievements before we look forward at his vision. Jim Keller is the CEO of Tenstorrent, one of the fast-growing AI systems companies that is driving not just the future of AI compute, but of open standards, of democratization through RISC-V processing architectures. And just recently, Tenstorrent launched its Ascalon RISC-V processor IP and Tensix AI IP as well, along with their open chiplet Atlas architecture. And we'll get more into that, but just a quick recap. As most of you know, Jim is a legend at processor architecture. And prior to Tenstorrent, he served as Senior Vice President of Intel Silicon Engineering Group, and he has held roles at Tesla's autopilot and low-voltage hardware program that he pioneered. He was a corporate VP at AMD and Chief Cores Architect, as well as Vice President of Engineering and Chief Architect at PA Semi, which was acquired by Apple. Jim has successfully led silicon designs over decades, from DEC Alpha processors to AMD K7, K8, K12, and the AMD Zen families, as well as the Apple A4 and A5 processors, not to mention Tesla's self-driving car chip. Now, I have had the good fortune of interacting with Jim in a number of his past roles, and even more so currently, as Jim happens to be the inspiration behind the formation of Baya Systems and currently serves as the chairman of the board. Welcome, Jim.
Hey, good to see you. Thanks for the intro. And by the way, it was A4, 5, 6, and 7. But for some reason, they won't put that in the Wikipedia page, and I don't know why. It's pretty fun.
Well, see, we always learn more every time we speak. So speaking of which, right, you've often said that good ideas start simple and then get refined by reality. So looking back at what we just talked about here, moved from a processor-centric set of roles at the DEC and then AMD and Apple to the AI-focused roles that you've had at Tesla and now at Tenstorrent. How has your approach to innovation evolved as systems have become more distributed and data-centric?
Yeah, it's really interesting. There's a book called the Systems Bible, I think it's like, which basically says you can't design complicated things, and I really like that. And then the sub rule is complicated systems, evolve to be that way either through an addition of features or combination of simpler systems. And then there's a corollary to it, which is you can't fix broken complicated systems. And so in designing modern computers, we used to do like a CPU as a chip, and then there was an integrated chip, and then there was a big pivot to go to IP-based chips. So you had a CPU as IP, fabric as IP, memory controller as IP. And every time you want to achieve more complexity, you have to sort of re-engineer for the component levels to be simpler, and then build it up with combinations. And in the last couple of years at Tenstorrent, we're building an AI supercomputer. We're going to basically have thousands of AI chips collaborate with millions of processors from very simple software stack. And to achieve that, we really had to redesign the software stack and make it layers. And then recently we've refactored our chip plans to be chiplet based. And we just figured out how to make our systems also much more modular. And so by making everything have the right abstraction layers and modularity, we can actually build really complicated things out of simpler components. And yeah, I think that's a pretty solid foundation for doing new things.
And that makes a lot of sense. And I think one of the key factors I've seen at Tenstorrent for a while is kind of the software 2.0 or software-defined hardware mechanism, which I think you're alluding to. And what, at least what we see is the traditional data center behemoths, which are generally CPU, have been replaced by GPU, but that's not sufficient, right? We're moving from core-bound designs to data-bound systems where performance depends not just on flops, but how efficiently data moves from nanometers on die to millimeters across chiplets to meters across systems, etc. So how do you see that changing the way systems are architected?
Yeah, so there's a couple of things. Like GPUs with extensions of tensor processors have been quite effective on running AI, but the scale-up part has been built around multiple layers of software, right? So, you have the program running on one GPU and another software layer, collaborating GPUs and another software layer. And I think that software stack is quite complex and takes a lot of people to manage it. And the thing I'm really into is, how do we build the layers of software in a way that, the programmer doing an AI model can simply describe what he wants and then use the layers of software to do it. So I think we are now achieving that. It's pretty cool. And then the other piece is the current data center. There's like a host CPU that runs a driver to drive the GPUs, and then there's a separate set of computers to quote do general purpose servers. And the thing I've been really interested in for years is kind of heterogeneous computing where the CPUs and AI processors collaborate together. And we're building an architecture. So we picked RISC-V so we can build our own CPU and we can connect it together with AI in a really flexible, novel way. I think there's a lot of innovation in this space. And like we recently announced Escalon, our high performance 8-wide out of order CPU. We're going to build a server chip using the Baya fabric next year. That's really cool. But the way that processor integrates in with the AI is novel. And I think it's really going to unlock a lot of creativity on how to build future software stacks.
And that makes sense. And in fact, as you've said, right, there's a lot of innovation ongoing on how data moves and how you actually combine these different types of processors, tensor, traditional CPU, etc., to get the best out of it. And I know part of what you kind of pushed us to do as well as Baya is to enable that software-driven design, right? Understanding of the performance required, and then address what the industry needs. If you can speak a little bit about, how analyzing performance and how actually building these larger systems require kind of a change in mindset and tooling to achieve that.
Yeah, it's really interesting. So fabrics used to hook a few things together, right? And then people build cache coherent networks, which are famously hard. And, and we scale them pretty far, but it's really complicated. Like, 64 core, 128 core cache coherent chips are remarkably hard. And that's probably because it's a lot of distributed state and all the components have to really know exactly what they're doing. Whereas network attached computer scaled really fast. And that's partly because it's, from a state point of view, pretty lightweight. I send you a packet, you keep track of packet counts, they don't have to know what each other is doing. And then as we go into chiplet-based design, we want to put more silicon together, but it can't scale in a way that's complex, like, let's say cache coherency and stuff. And then the AI mostly doesn't care about that. So the Baya fabric, we started tops down to say, how do we build a fabric that naturally works with chiplets, does on-chip interconnect, does cache coherence locally where we need to. Like I really like that design. Sometimes data is moved by the big processing agents themselves. 10th-order architecture, we actually have multiple CPUs in every AI cluster. We're doing our future general purpose CPUs the same way. So we'll have CPUs that run programs and stuff, but there's also additional CPUs. We have software defined data movement at any layer. The weird thing was when we say data sharing, sometimes we really mean data sharing, but sometimes what we mean is we have this very large data objects sharded across a very large number of processors. And then as the processors are computing on it, they want to have a very natural method to continue to exchange the updated partial products, to move the data around, to use the different processors' memories as a way to keep all the data. And that's where you have the fabric layer, the data movement engines naturally talking the software to coordinate this big stack. And it's sort of we building it layer by layer. And again, my short-term mission is to have 1,000 chips, 1 million processors, collaborating on very large programs in a heterogeneous way from a very simple software stack. And I think it's happening. And it's quite something to achieve.
I think that's actually has been a very exciting time for us as well, looking at the combination of coherent processing systems alongside AI fabric that, as you say, is not really necessarily state sensitive as much. And I think as we'll get into the chiplet discussion in a short while, but that also then looks at all the memory, caching, et cetera, you need to carry if you're doing fully coherent systems. And that obviously breaks down as you start going across multiple chiplets, et cetera. You have to think about it differently. Do you want to care to talk a little bit about, especially for the approach that you're using for AI, right? Which is, there's always a difference between compile time and runtime, which actually makes this quite different. You can always build a very efficient processing system if you know exactly what at compile time, but AI loads are always changing. Do you want to tell us a little bit about how you guys are looking at it?
Yeah, well, so this is, AI is really interesting because there are parts of it that look very, very much like compile time. You figure it all out, just what to do. And people, often say, well, if you just have this set of matrices and you know exactly when you're reading and writing all the data and, it's going to be deterministic. I don't think that's true in general. Mm-hmm. There's like local details, like you're doing computing and, you're taking advantage of sparsity. The data is really uneven. You're constantly changing formats. You may not even compute some kind of data. So it's not that, stable. The mixture of experts world says you're building these big collaborative AI models, but which experts you fire up, that's dynamic based on the computation in the matrix. So that's an interesting thing. You have all this variable length inference change combined with batching. So that gives you another kind of dynamic stuff. But the thing that's starting to happen is as the AI is working for you, it's generating requests into databases, into general purpose computing. You're going to have the AI generating programs, which are then going to run on data to summarize it or bring it back. And long run, it's going to be a very dynamic computer. With some things are stable, like we assign these processors to do this kind of thing, and we're laying out certain kinds of databases in certain ways. But boy, the access patterns and the compute patterns are going to be really dynamic. And your software stack has to deal with that. And it's way, way too big. Millions of processors, it's way too big to have cache coherency. So.
Yeah. And I think what you were talking about as well, I think we all look at AI as, being gearheads, at least on my side, we originally looked at AI as a hardware problem. It's not. It's a full software and system problem. And where you kind of know things compile time versus where you know runtime is actually where the difference is. And that's where I think what I'm seeing from TensorStorm is the abstraction layers, the software that needs to be handled at every layer to simplify that is, I think, the big step, right? I think.
Yeah. Remember, it's the layers that need to be simple. I give this talk periodically. It's like humans aren't getting smarter, and like technically we're not that smart. And so we can't solve really big, complicated problems, but we're pretty good at breaking problems down.
Mm-hmm.
And then sometimes you see software stacks that obviously have too many layers in them, and they spend all their time fighting about the abstractions. But more often, things slowly turn into a big ball of mud, which is a famous computer science paper. So if your listeners want to go look it up, just look up big ball of mud. It's great. And then knowing when to refactor and how to make the layers properly and how to keep things, simple enough that we can make progress. That's really important. But the top to bottom stack it's amazingly complicated, especially when you're going into bigger systems. I think the challenge of doing small inference models on single chips is sort of getting solved. But doing very large models, inference training, and the dynamic computational systems that we're building with pretty big scaled systems, that's a lot of work.
Yeah, and as you said, right, breaking down the problem and chiplets, for example, as we transition, is one of those ways to break things down, right? Complexity and scaling, you want to break it down to chiplets, breaking the reticle wall limits or balancing yield and flexibility. When you started at AMD with Zen, right, I think it was designed from a very modular mindset, which lent itself to chiplets, even though I think the first time it came out was probably a little after you left, but the design was built that way. Now at TensorStorm, you kind of embraced that right from the beginning. And what would you say you've seen change in the last decade or so since the Zen microarchitecture started? And how do you actually see this transforming? Because traditionally it's been kind of vertical stacks with companies that have built it internally, but in the future you'll have to actually start getting chiplets from best-in-class players and pull it together. So what have you seen change in the last decade, and what do you think are the challenges still outstanding?
Yeah. So, when we built Zen, we had to build our own chip-to-chip PHY. And the first, at the desktop and server level, we made a chip which actually had CPUs, PCI Express, a memory controller. But to accomplish the roadmap, we built it so you could hook 2 or 4 of them together. Right. The second generation of Zen is they built, basically the I/O memory die, and then which had all the interfaces for all the memory, because people, they wanted to have a scalable memory footprint, but we did that with numbers of DIMMs. They wanted always a fairly large number of PCI Express lanes, but a variable number of CPUs. And then they went to a 2-chip architecture with a CPU die and a base die. But they're still building a custom die-to-die PHY. First with a bunch of wires, and in UCIe, there's a standardized, chiplet PHY, which is now being used. But the architecture around, like, how do you define a chiplet? How do you build it for test, power management, negotiation? That's something that's actually fairly complicated, and building the framework for that. And we looked at groups, working as committees to go do that. And I was not really satisfied with the speed of iteration and then the number of technical problems you have to solve. You have to solve 1,000 problems. You can't meet once a quarter to talk about them. 1,000 problems needs, a team working and meeting every day to solve them. So we built our own chiplet interfaces we picked a bunch of wires definition because we really liked the team that was building it. They had a really good power and speed trade-off. but they're also really flexible and open to go work with us as we solve those technical problems. And then Tenstorrent acquired Blue Cheetah, and that's now part of our team. And I think that's going to work out really well for us because now I can guarantee multiple generations of chiplets to be compatible both for me and for some of my, partners. So I'm really into that. But building that chiplet frame and making it work and then building the collateral for that. We named that Open Chiplet Atlas. Atlas is a thing that holds up the world. And there's way more to it than a spec. It's not a PowerPoint problem. It's, there's all this IP to support all the different features, whether it be test or power management or negotiation or, like configuration of the actual transport methods. So we built that and we published it. We published support IP for it. We're publishing verification and performance environment for that. And I really want that to be open. Now, it's open in the way that we're building it for ourselves. We're guaranteeing it works. We're publishing the collateral that goes with it. And we're really open to input and collaboration on it. But it's not currently like an open committee where people go vote about it. Because I think really in the next couple of years, there's a lot of innovation that has to be done and it needs to move pretty fast.
Right. Now, I think I have a couple of kind of follow-up questions on that. Clearly, but I'll stick to the one that you just mentioned. Committees are good for standards that stabilize, but not necessarily for speed, right? And I think now,
that's the traditional thing, and you can see like Ethernet and PCI Express have often worked, but sometimes the next generation was years late compared to the need, and sometimes they kind of accumulate features. Standards around like Rocky and Ultra Ethernet and stuff have not worked out very well. The committees kind of add lots of features and don't really deliver the right minimal set. We saw this happen with CXL. Like a whole bunch of stuff in that spec is pretty good, but it became way too big as a spec and people did too many different things for the compatibility. So I'm always interested in how these things work. Like JDEC has often worked really well for DRAM definitions, but not every time. And also some of the features that we needed in DRAMs never really happened. So.
Yeah, I think, being past life at Denali a while ago, etc., I saw JEDEC close in. And I think there was a lot of movement in the early days where there was so much to be done that everybody wanted to get done. As it gets more defined and features start getting somewhat more esoteric or specific, I think that cohesive's not there.
Yeah.
But one of the questions I would ask, right? So naturally, obviously interoperability and things like that are a problem for chiplet architectures. But alongside that, you also have you're expecting to build a chiplet ecosystem. Okay? And now there are arguably competing standards, if you will, such as ARM's chiplet specification architecture. Right? I think if these have to kind of coexist or potentially bolster each other to kind of grow the market, how do you see that happening?
Well, we'll see how it all plays out. We're building 3 chiplets we're taping out at the end of this year, and then we're doing 3 or 4 next year. We're still trying to nail that down. I think it's going pretty well. They'll all work together. We're publishing all the architecture and collateral you need to go build your own chiplet. And if somebody wants to co-simulate with us, just call me. It's super easy. We'll co-simulate. If somebody needs die-to-die PHY, call me. It's going to be super low cost and super easy to do. So we have a big stake. Like these chiplets have to work. We depend on them. And I want to make them work for other people. And my business isn't making money on chiplet infrastructure. My business is, making AI and compute solutions in a variety of markets, and partnering with people who are into our AI processor, our CPU, or our scale out subsystem. We're going to be really open about marketing it. So, and selling it and supporting it. And like I said, co-simulation is really fun. Like the RISC-V, the ecosystem is a good example of this. So they have a steering committee. They published RB23. It was a year late, unfortunately. It was kind of a pain. But then Tenstorrent independently published an architectural test generator. We support the reference model. We've added a whole bunch of features to it. We now have our Escalon processor up and running in a HAPS box, for pretty low cost, and it's really easy to, use. We have customers, logging into it and just running stuff on it, and we can deliver that. So, yeah, I think the proof will be in, who's really open, and also our architecture, we're publishing in a way that if somebody likes it but they want to make their own changes, go ahead. I don't care. And if they want to contribute to changes and that works, great. If that all works out, we'll take them. It's like a real open source model. Linus Torvalds controls Linux, but people submit software to him all the time, and he takes some and not all. And sometimes there's pretty big branches because he didn't want to do it, or it wasn't the right thing at the time. And I think open source should be flexible in that kind of way.
So I think you kind of transitioned to the right spot I was getting to, which is, you've been a champion for open ecosystems, and this last 5 to 10 minutes have been specifically focused on that. So I'm going to make one quick check so that people fully got it, right? Which is, even for the chiplet infrastructure, what you're saying is interoperability, which is generally a challenge for die-to-die interfaces. You'll enable them with the Blue Cheetah files if you need to, with co-simulation, so that if that's the main bottleneck, you've kind of taken that out.
Yep.
Right.
Yeah, and the architecture is also done in layers. And if somebody wanted to use, our open chiplet architecture, but swap to PHY, they could. It just wouldn't be compatible with some of the chiplets I've built. And I actually have a customer who wants, my family of chiplets to work with his, but he wants on the other side to have a UCIe interface. And so I think we're going to integrate both PHYs. It's a little more cost and it's a little more cumbersome, but, there's ways to make this work out. And I think, people start to envision we need to grow this ecosystem. Well, actually, we need to make it work first. We need to have some good examples of chips in a different process, maybe built in a different year, that are compatible. And, how do we build, because specifications always add new features. How do you make backward compatibility work? I think I have a lot of work to do on this kind of stuff. And I'm not in a big rush to worry about growing the ecosystem or worry about multi-vendor compatibility. I want to demonstrate a family of chips that work together, that you can package together. I'd love to have a couple of, small partners, to be honest, who would like to have a lower cost of building their new silicon dream. And then we'll support them and learn a lot about, what does open source architecture, what does co-simulation environments mean? These things are pretty hard, because once you commit to silicon, you've spent a lot of money, and you sort of, pull the trigger you can't return. Software open source, you mess something up, you put a patch in, everybody downloads it, they're all good the next day. Hardware, it's a bigger lift, and it takes a lot more thinking. And I think it's going to take a couple generations to sort this out.
Yeah, I think, as you said, right, the proof's in the pudding. If you make it work and demonstrate it can be done, you've also learned along the way how to take it to market for the broader ecosystem. And from our standpoint, right, we kind of look at it the same way as well, because when you do the partitioning across chiplets or understand how they're going to be working together, you do need the software capabilities to understand performance across clusters or across boundaries. And a lot of what we're seeing in the market is really driven by customers wanting to understand how these two things are going to work together well before they even start down the path. And then also sizing up what their PHY needs are. If you frame it right, can I do it with a smaller or a lower cost, lower power PHY, etc. So we're seeing some of that. And certainly there's a lot of learning going on all sides at the moment. So I think I'll kind of transition towards your path towards, I think, the sovereign engagements that you have, because they seem to be all building up not just an ecosystem, but kind of a momentum around different processing elements that are somewhat more open source or collaborative, right? So you've announced a number of engagements with countries like Japan, Korea, and others. Do you want to give us your kind of both the philosophy as well as how you're going about doing that?
Yeah, like quite a few people come to us and they say, we want to be able to own our technology, because we're often spending billions of dollars on technology. And they're wondering, like, am I going to be able to have it next year, iterate on it? And then quite a few regions of the world, they're basically sort of powering up in their tech stack, right? Mm-hmm. And they've been buying computers from Intel, NVIDIA, IP from ARM, but they would like to have local technology. And it turns out there's a lot of entry points. Like India's been doing a great job for years doing design services, CAD tools, IPs, but they haven't really built a big semiconductor company. So it's really interesting how these pieces come together. So Tenstorrent, we're building a full stack. So we build IP, chiplets, package parts, board systems. We have cloud software, AI software stack. We're building models and we're firing up our training computer. And partly that's to use our IP and software in the full stack. That proves it works. We can demonstrate it. But there's a whole bunch of applications. Like we license our AI processor to LG to build televisions, to Boss to build autonomous driving chips. A number of people are really interested in the triplet infrastructure, because if you want to build your own servers, starting by building boards and packages, but licensing chiplets, that's a really great on-ramp. Or you want to build a new network chip, but you want to license a CPU and AI, that's a great on-ramp, because you don't have to do everything to get going. And I think that's both a good business, but also, for a small company, that's something we have to offer. Like I'm not trying to control market share or maintain really high margins. What I'm looking for is customers and partners that are up for this technology stack. And
basically you're enabling, you have all the key components that you can enable partners with to do their own innovation.
Yes.
And I think that dovetails so well with what we're trying to do as well, which is enabling from the top down the ability to build systems for Baya's, Beaver Pro, etc., to analyze and then customize so that it's fit for purpose. And I think a lot of the emerging markets are looking for not just a one size fits all or giant compute centers, but really fit to purpose, fit to cost, fit to energy efficiency budgets, solutions that are still utilizing the benefits of the software and open source ecosystem, the IP such as RISC-V cores, 10.6 cores, and of course, system IP to do that. Right? And so from your standpoint, you've seen a lot change, especially in the RISC-V world over the last 3 to 4 years. What are the current bottlenecks there, or blockers, or do you see it's really gaining that momentum, hitting critical mass?
Yeah, so RISC-V started as a university project, and they did something pretty remarkable, which is they made pretty good 2 wide in order, 3 wide out of order processors, the Rocket and Boom cores. And then enough support collateral, it went through all the universities. So if you're doing computer architecture today, your go-to platform to experiment is RISC-V. And I'm really amazed. And, those guys did great. Then RISC-V started growing with companies like Andy, Sci5, Ventana, some others. And then several areas of the world, EU, India, Japan, China, said, we're going to use RISC-V as a platform for the future, right? So then it needed a whole bunch more collateral. And Tenstorrent has helped out with architectural reference models, test generators. We did a lot of work to uplift native compiler performance, and it worked out really well. The architecture is quite good, and the compiler, just needed somebody to really work on it and uplift it. Linux support is actually quite good. Driver support's good. Android has been lagging. There's some people working on it. I think that really needs some work. There's a couple of places where we need the right reference silicon. So we're building a part called Atlantis, which uses Escalon. It's a general purpose part. It's not designed so much, to really nail performance, but to be a really low cost development platform. So we're going to sell those at really low cost next year. That project's going really good. RISC-V needs a 10-pole server silicon. So we now have a really great plan to go build a high-end server silicon. I think just as people use it and elaborate the ecosystem, like we have critical mass. There's multiple companies using it. RISC-V, if you just need a general purpose processor embedded in your solution, it's a go-to because, the cost and support is really good. I think it's mostly just like keep turning the crank on it. Now, part two is computer innovation is about to take off, right? And RISC-V is the platform where anybody can do something. Like ARM, you license the processor, the architecture is okay, but you're not allowed to change it. Obviously, Intel and AMD, there's no open source architecture ecosystem at all. So periodically when you hit an inflection point, the things that people can really own, modify, and change are where it's going to happen, just because that's where you can, right? So we open sourced our Tensec architecture. So Tenstorrent built an AI processor, and we released all the software stack. And it started with a kid reverse engineered our AI processor in great detail from our software and published the spec. And I thought, that's amazing. We just published our AI architecture. And then some of my guys found some bugs in it, and they said, what should we do? And I said, well, let's send them bug reports. So we did that. So now we are building a really great reference model for the architecture. We're going to publish that pretty soon. We have some more work to double check accuracy. That means there's a reference architecture spec and a reference software model and a software stack that you can use openly and then go modify however you see fit. So that's an open architecture. And I think I'm fine with that. So RISC-V is the open CPU architecture. Tensec will be the open AI architecture. And then if you're a student, you want to go mess with something, you can buy a low-cost Tenstorrent hardware to go run it on hardware, but you can also have a reference model, a software stack, and you can go play with it. And I think it's really great that people can go do all kinds of experiments. I plan to take advantage of them, and I plan also to do a whole bunch of innovation in that space over the next 5 years.
So a very topical question here, right? So if you were mentoring the next generation of architects, which clearly you've seen a lot of that innovation happen, and as you said, people are reverse engineering, putting it back, and it's becoming a much more almost snowballing into broader innovation. And if you go back 20 years to now, what would you advise or mentor an architect starting on their journey today?
Oh, it's really easy. Work on stuff that's open. So you can use it, modify it, collaborate it, publish it, share it. Work in a small company, right, where you can have a really big impact. If you're a student now, get a really good internship, 1 or 2 companies, so you can get exposed to or if you go to the same company, make sure you're in a different group so you can expose to, different ideas, attitudes, management styles. And be really hands-on. Don't go someplace where you're pushing PowerPoint and going to meetings and spending 2 months justifying the change. You should be writing code, doing commits every day, working to get something released. Like the world is designed for speed, and AI really accelerates speed. So if they go in and they're all writing classic C++ programs or Verilog, you're in the wrong place. Our guys have multiple AI windows up and running. We generate code really fast. We use it to refactor code. So make sure the company is thinking about velocity. And, not everybody, but mostly that means smaller companies. And if you're in college, get some internships and learn some stuff. We have a lot of interns. They're amazing.
That's fair. So I think one quick question I was going to ask, because we're blowing through a lot of good discussions and and probably running on your time constraints as well. So what currently we've seen with scale up, right? And Baya especially started seeing a lot of pull through traditionally to go through newer scale, which is architecture, to change crossbar architectures to make it scalable across chiplets, et cetera, and as you talked about, how if you get to millions and billions of processors, how do you see the scale-up market going, and what do you see especially from what would you advise Baya to go do, for example, for that?
Well, you guys have a pretty good architecture top to bottom. So elaborating that, getting more customers, making sure people can go from like architectural concept to performance of the architecture to go building it really fast to make it work. We did a couple of POCs with you guys, and it was really fun that we could decide what we're doing, analyze it, bring up something pretty fast, and then, iterate on it. The implementation of silicon it's really tough currently. Going from, I got the Verilog and the architectural model running to I have a physical instantiation of it in a chiplet. I think we need to do a lot of work on that. Existing CAD tools are great, but they're slow, cumbersome, and we need a lot of innovation around the whole design exploration space and speed on that. So yeah, I like what Baya is doing. Obviously, I'm part of that. But the ability to go from concept to silicon faster, I really want to work on it. We're working on a couple of chiplet projects, which I think are going to be remarkable, both in terms of speed and cost. By dividing, conquering the silicon, I don't have to boil the ocean on the memory controller every time. I can focus on memory controller chips that, do something new and interesting, but then I can attach them to the CPU or the AI or the network to switch. And I really want the pieces to be independent so they can move fast. And yeah, so I think we have work to do on the speed.
Yeah, lots to do, but fun stuff to do. I guess we're approaching this new equilibrium, right? The traditional focus of AI has been on the brain or the compute, but even the brain itself is a collection of trillions of compute elements. And more importantly, what we're actually talking about with AI is really a nervous system that connects it all together to go from sensation to cognition, which requires both context, causality, and connectivity. Mm-hmm. So I had to try to throw it into Baya's metaphors, if you will. If compute is a thread and connection is the weave, we're focused on helping build strong, intelligent fabrics. So with that visual, I think, Jim, this has been a fascinating conversation. You've kind of gone from compute, connectivity, to chiplets, to creativity, to cross-continental collaborations, all that are reshaping the future of AI. Well, thanks again for making the time, and wishing you the very best in enabling your vision, and we're part of it.
Yeah, great to talk today. Appreciate it.
Thank you for listening to TechThreads, Weaving the Intelligent Future podcast. Join us monthly for insights into the evolving tech landscape and the future of chiplet technology. If you enjoyed today's episode, don't forget to subscribe and share it with your network, and stay tuned for more expert discussions. Let's weave the intelligent future together.